This is a review of one-dimensional motion, specifically the velocity and acceleration vectors and their relation to each other. So first of all, let's just go through our notation here. We have v with an arrow over it, and that just means the velocity vector. It doesn't specifically mean that velocity is going to the right always. And the acceleration vector with an arrow over it, again, just showing that acceleration is a vector quantity, not necessarily that it is always to the right. And then we have the equation for acceleration. This is really just the definition of acceleration in equation form. Acceleration tells us how quickly the velocity changes. So first of all, to have an acceleration that is non-zero, you have to have the velocity change. Remember that velocity is a vector, and so vector quantities have both magnitude and direction. So we either need something to change about the magnitude of velocity, how long the vector is, which indicates the speed of the object. The number part essentially is what the magnitude means, or the direction, obviously, then the direction of the arrow. So acceleration is a vector quantity, velocity is a vector quantity, change in velocity is also a vector quantity. So if acceleration is the change in velocity divided by the time interval, delta t is the time interval, then if acceleration is a vector quantity that has a direction associated with it, it has to get its direction from the delta v vector. It can't get its direction from the time interval because time doesn't have a direction. It doesn't make sense to say it's left, right, up, down, north, south. But change in velocity is a vector quantity. So if you can find the direction of the delta v, or the change in velocity vector, then you know the direction of A. So let's look at a couple of cases just for horizontal, well, 4 cases, just for horizontal motion. So the first one is if our object is moving to the right, and each of those vectors represents the velocity at one particular, after each time interval goes on. So this is really just a motion diagram, right, showing us how far the object moved, which is then just going to be proportional to the velocity. So those are 4 velocity vectors. Now, in order to find the change in velocity vector, that's what we need to find acceleration, we have to redraw v0. I just picked it up and redrew it. It stays the exact same length, it points in the exact same direction. Redraw v1, I picked, it points the exact same direction, exact same length. It's like you're just picking up that vector, that arrow that is over v1, and you're redrawing it. And now in order to find delta v, you have to decide what do I need to do to v0 to turn it into v1? Or more generally, what do I have to do to the earlier vector to turn it into the later vector? In this particular case, to turn v0 into v1, right now their tails are already in the same place. So the tails are kind of pinned in place. They are together. The starting points are together. In order to get the arrowhead in the correct place, I need to take v0 and make it longer. I need to extend it more to the right. So that's what our delta v vector looks like. So delta v points to the right. It has to make up that difference. So if I took v0 plus delta v, it would become v1. Think of delta v as what do I have to do to the earlier vector to turn it into the later one. If delta v points to the right, then that means that A points to the right. Next case, we have our object is moving to the right, but now my velocity vectors are getting shorter. So I pick up v0, I pick up v1, and I just move them so that their tails are lined up. And then what do I have to do to the earlier vector to turn it into the later vector? In this case, I have to make it shorter. So I have to push that arrowhead in so that v0's arrowhead ends up where v1's arrowhead needs to be. So that's my delta v vector, which points to the left. Therefore, A points to the left. Notice that A has nothing to do with the direction of travel. The velocity vectors tell you which way the object's going. The direction of A does not tell you which direction the object's going. In the second case here that I just did, v0 points to the right. The object is moving from left to right, but the acceleration vector points to the left. A doesn't tell you which way the object's going. V tells you which way the object's traveling. Okay, next case. Our object is moving to the left, and those velocity vectors are getting longer. So I'm going to do the same thing. It's getting longer in a steady way. So I'm going to pick up v0, which is the short vector, redraw it. V1, which is a longer vector, what do I have to do to V0 to turn it into V1? I have to make V0 into a longer vector. So that means that's the direction of delta V. Direction of delta V gives you the direction of A every single time. If you know the direction of delta V, you know the direction of A. A matches the direction of the delta V vector, not necessarily the direction of the velocity vector. Notice that V and delta V sometimes are in the same direction, sometimes not. Here's another example, last case. Moving to the left, but these vectors are getting shorter. Shorter by the same amount every time. So I need to redraw V0. It's a long vector. V1 is a shorter vector. What do I have to do to the earlier vector to turn it into the later vector? It's not just make the short one longer. Find which one is earlier in time, which one is later in time. Turn the earlier one into the later one. So it has to get shortened, pushed in. That's the direction of delta V. That's the direction of A. Okay, so let's just look at some patterns here, what we see. Does velocity always match the same direction as A? Nope, there are two cases on the right where it does not. V and A do not have to be in the same direction. Sometimes they are, sometimes they aren't. Delta V and A, do they always match direction? Yes, delta V and A always match direction because that is the definition of acceleration. It has to do with the change in velocity vector. But you know the direction of delta V, you know the direction of A. Do we see any pattern between the between the velocity and the accelerations? I see two cases on the left where velocity and acceleration are in the same direction. In the top left example, they're both pointing to the right. In the bottom left example, they are both pointing to the left. What happens to the object when V and A are in the same direction? Constant speed or changing speed? It's got to be changing speed. And is the object speeding up or slowing down? Well, in both of those cases, the object is speeding up. Let's look at the right two cases. I have velocity and acceleration in opposite directions for those. And what do we see the object is doing? Slowing down. Okay, so let's summarize. In the top left example, velocity is positive, which just means the vector points to the right. The object is moving in the positive direction. Acceleration also points to the right. And you can see that that object is speeding up. Let's look at the next one. Velocity is pointing to the right, therefore that's the positive direction. The object moves to the right. Acceleration, though, is in the negative direction. What do we notice about that object? Slowing down. Next example, we have velocity is pointing to the left. That means negative velocity. That has nothing to do with whether the object is speeding up or slowing down. Negative velocity just means that the object is moving in the negative direction, which is to the left. Acceleration also points to the left. What do we notice about that object? Speeding up. Bottom right example, velocity is to the left, so that's negative. Acceleration is to the right, so that's positive. What is the object doing? Slowing down. So even though acceleration is positive, in this bottom right example, the object is slowing down. So another misconception we want to make sure is clear. Positive acceleration doesn't mean going faster. It could be. Top left example, we have positive acceleration and it's going faster, but it's not a rule unless it's always true. So bottom right example, we have a positive acceleration and the object slowing down. So let's look at it as something that will be always true. The examples on the left are both cases where the object speeds up, either is moving to the right and speeds up, or is moving to the left and speeds up. What do we notice about velocity and acceleration when the object speeds up? We notice that V and A are in the same direction, whatever that direction is. They could both be to the right, that means faster and faster to the right. They could both be to the left, that means faster and faster to the left. So our general rule here is if V and A are in the same direction, whatever that direction is, the object will be speeding up, will be going faster. Correspondingly, velocity and acceleration are in opposite directions, as in the two examples on the right column. Then what do we notice about that? Slowing down. So no matter what those directions are, if V and A are in opposite directions, one's to the right, one's to the left, or the other one's to the left, the other one's to the right, then the object slows down. So we want to make sure that we don't think about positive acceleration means go fast. You wouldn't know that unless you also know the direction of velocity. Velocity and acceleration in the same direction, the object will be going faster and faster in whatever the direction of V is. V and A in opposite directions, the object will be slowing down in the direction that the object's moving, which you know from V. I hope this is helpful. Please let me know if you have any questions.